Auger, duality, TGA, everything else that you might want to know.
Okay. So first, the title is not correct. So really, the deep content of this paper, which is by Yankee Lakili and Tobias Eckel, has really nothing to do with Lagrangians and Lagrangians. It has only to do with Lagrangians. And so, yeah, but then I'll try to explain why they call it like that, and it has to do with surgery formulas. So what I suggest is that we get to kind of the main example that Floer theoretical we do understand, which is the cotangent bundle. So this is, I think it's fair to say, the only example that Floer theoretically is completely understood, and it's non-trivial, so it's not so critical. And in here you have two Lagrangians, which are pretty nice. So the first Lagrangian, which is compact, is given by the zero section. So this is a compact Lagrangian, and it can be endowed with whatever structures you want to endow it with. And then there's an exceptional second kind of Lagrangian, which is the cotangent fiber. And let's call this F. So, okay. Now, out of these two Lagrangians, you can try to do Floer theory. It has not been reviewed in detail, but essentially, for a compact Lagrangian, initially this was all coming from the Hamiltonian Floer theory, where you actually wanted to count, well, fixed points of Hamiltonians or orbits. And at the end, the goal was to relate whatever weird thing that was counting orbits actually was Morse theory. And because then you knew the Morse theory had some generators, then it had to have orbits. And somewhat we've really differed from that way, which has been the last decades. And now kind of we just like values reflecting invariance on their own and kind of forget that they're Morse theoretical in nature. So today's talk is sort of, we really haven't gone that far. We're still doing, in a sense, very hard Morse theory, but it's not really new. So the first thing I want to say is that for a compact Lagrangian, you have the Floer cochain complex. So those are generated by the intersection points, as we have reviewed, and you can start counting disks in order to endow this with the product, and you can start counting disks which, for instance, start at 2 points, at 2 intersection points, and go to a third. So this would be two inputs and one output, and mu1 would just be the usual differential like that. And this constitutes an algebraic invariant by Hamiltonian isotopy. So the second invariant you can associate to F is this RAP homology that we're discussing today. So that's the RAP homology of F. And this guy is going to be generated by intersection points of F, and then the other F wrapped around infinitely many times by the rep flow. So with then RAP F, bit bigger. Okay. Okay, sorry. Well, you know this.
So now F is not non-compact, right?
F is this, yeah, okay, so, okay, let me draw this. So, in here you have this Lagrangian, okay, and in here you have the other Lagrangian, which is exactly given by this. So this is F, here I'm drawing this star of S1, and this is L in here, okay? And because both are depicted in blue, there must be some relation between them. So what's the relation? Well, let's try to see what this complex is. Well, if I perturb this by a very small Hamiltonian, at the very end I just get a Morse function. So this should essentially be just the the Morse cochain. So this should recover the cohomology of L. And then what should this be? Well, this is slightly more interesting. The endomorphisms of this F in the Raphokaya category actually recovers the chains, or to be completely precise, the negative graded chains on the loop space of the bundle. So in this case, it's going to be L or M, whatever you want to call it. In this case, it's going to be S1. Okay, we kind of saw that in the talk in which, in Sebastian's talk, in which this thing was wrapped around in here, gone around and again, and such. So in here, what we saw is that we had this initial point in here intersecting the blue guy and the green guy, and then we had the second intersection point here, maybe x1, this is x0, this will be x minus 1. And then you can try to count the differential. You'll see that there are no differentials, but there's one product, which is this guy and this guy, so for instance, this guy with, say, this guy gives this guy. And what you have to do is you have to find a triangle here. It's quite a good exercise to try, and otherwise go to the universal coverall and you'll see the triangle.
I'm sorry. You just made some statements on the chain level, right?
Yeah.
Just to yeah.
Yes, so so this is a chain level statement about A infinity algebras. Okay, so in here it's very clear how you recover the loop space, and in general what you can think sort of is that the Reb field in a sense is a geodesic field, and now if you've read Milner's book on Morse theory, you can understand that the loop space has some models in terms of geodesics. So it's not unreasonable that this kind of information on Reb, when you take chains, you actually kind of finally approximate the loop space, and actually you recover out of this complex the loop space of that guy. Okay? So okay, point of this picture in here, of this blackboard, is you have a compact Lagrangian, you have a non-compact Lagrangian, you compute Floor chains in here, you compute Reb in here, and it happens that they're related. How are they related? Well, I don't know. But let's call this duality, okay? And the point is, in which sense this is a duality? Okay, so this is what will be called Koszul duality. And the goal of maybe the first 10-15 minutes is to understand in which sense these two spaces are dual. Okay, for that I'm going to go and do some extremely basic topology, which is, okay, why would the loop space of L, or L itself, or the loop space of a topological space and itself, be related in any sense, or in a sense have a nice pairing? Well, the key idea is a geometric one, which is that we have the path vibration. That means that there exists, for a given base point, in a topological space X. So this X has nothing to do with that X, it's just another topological space, maybe M. So for this M, you can include this into the path space. So this stands for maps from S1 to M. This stands for maps from the interval to M, such that the 0 goes to X0. Okay? So this space, does everybody agree this space is contractible? It's just subtracted to the base point. And then this projects onto the space X itself. So, yes. That projects in here. So, in a sense, these two are dual, because, if I try to compute chains in here and I try to compute chains in here, well, you might expect that this actually computes chains in here. Okay? So, in which sense this is true? Okay, so whenever you have a vibration, so suppose we have something like F is included inside of M, which projects into the base, we could try and recover the chains on the big space in terms of the chains of F and B. So recover, let's say maybe now, chains on M from, is large enough, Danny? It's great. Okay. So now let's see how fancy you are. What's the answer to this question? How do you recover the cohomology of a total space out of the fiber and the base? Yeah, you're very fancy. So it's good. No, it's good. I mean, the point is that the spectral sequence actually it's extremely beautiful device, but really historically that's how it happened. There was a very neat idea by Brown, which actually was like, well, imagine this was a product. I can just take the tensor product of this guy and this guy, and then you apply Eilenberg-Silber, which just says that the homology of that is going to be a quasi-isomorphism, so you prove Kuhne's theorem, which just says that the homology of the chains is the chains of the homology. Okay, great. So what can you do? Well, now you can twist. So the idea, I mean, your answer is perfectly correct. Then Brown has a paper saying, whatever construction we're going to do, that's exactly the same as Serre spectral sequence. The point is, Serre spectral sequence actually has to go, in a way, through this construction anyway. So, okay, so what's the idea? The idea is that we have monodromy. Or if you're an algebraic topologist, homotopy lifting property. So how could you express this? Well, what this is saying is that whenever I go in a loop in B, then I get some action on the chains of F. So this is telling me that there is a way of taking the chains of the loop space in B and letting them act into the chains of F. Good. Now, do we agree that there's a very natural map from the chains of B to the chains of the loop space, just by saying, well, whenever you have a loop in here, that declare it to be a 0 simplex instead of a 1 simplex. Okay, so there's a natural map from here, just decreases the degree by 1. So now the goal is to recover the chains in this total space M as some deformation of the tensor product of F and B. So now the idea is the form the tensor product of this using the monodromy here.
Sorry, this monodromy is sort of like homotopy lifting property, or?
Yeah, it's a geometer which is a connection. Algebraic topologies would say there's homotopy lifting property and such. So, and here the key word that you have to Google is twisting cochain. So that's what a twisting cochain does for you. So what's the idea here? Well, suppose that we incorporate.
So you suddenly jump from chains to cochains.
Yeah, but I mean that's the name it has. I mean you can call it system chain. It's a cochain in some other complex, so it doesn't really matter. So suppose that we incorporate the monodromy as follows. So you take the tensor product of B and F. Now I'm probably going to start having to dualize things, but it doesn't matter. Take the diagonal map. This is just going to give you another copy of B, and the only purpose of the second copy of B is to be used as the monodromy. So you have these things in here, and now, so this is the co-product. So this is diagonal map. If you're using certain chains, you have to do an Alexander approximation, but just assume that this map is well defined in singular homology. And then you get a second map in here, giving by the inclusion of the loops. So this is going to go here. So this map is here. Okay. And now the key point is that this acted on here. So now we can use monodromy. Okay. So now you get a map back in here. Where now you've used the monodromy. So we should agree that the structure of the fibration defines a certain map, like this, and that map encodes geometrically the monodromy of the fibration. We good with that?
Is it obvious that if we take the trivial vibration, then this map is trivial? Or
Yeah, because this action is trivial.
yeah, but it's not obvious what the coproduct does.
What the
Diagonal.
this is diagonal, and then you just
Okay,
act
yeah.
trivially in there. Okay, so this encodes monodromy. And what may be non-trivial, if you haven't seen enough algebra, is that actually this map can now be defined in order to twist the tensor product here with another differential. So in here you had a differential, which was just the differential in here, tensor the differential in here. But now you can add to this differential this map. And now somebody tell me, what do I have to ask for this map in order for that differential to square to 0?
So can you repeat the question?
So, okay, now consider these chains. Okay. But instead of taking the standard del, just take the del that you had, like the old time del, plus this map. Let's call this. I don't know how can I make it obvious. Let's call this M plus M. You know, and that's a twisting on this structure. Okay. So what I'm doing is I'm just trying to algebraically recover this by geometrically realizing everything, and then saying I'm just going to take this and deform it with M. Now there is a condition in M, which is this should square to 0.
Well, I don't know, m should square to 0 plus some commutation relation.
Yeah. So M should be a Moray-Cartan element. Okay. So this is you choose M such that this is a Moray-Cartan element. So okay. That being said, this is what's going to happen in this paper with the wrap homology and the Fleury chains. It's just that this Moray-Cartan element for us will be constructing counting pseudo-holomorphic curves. Okay. Now the monodromy is no longer going to be purely geometric. It's going to be purely geometric plus some kind of counting. Okay, and that's going to give you this element, which then is going to allow you to recover the cohomology or whatever first theoretic invariance of the total space. And then if they happen to be 0, well, then you call this guy and this guy Kosul dual. Okay? And the point is, the most obvious two examples that you can think of, this guy and this guy, will actually recover all this construction. Because essentially there are barely any curves in here. Okay? So, okay. Let me try now to do a bit standard geometric picture. Oh boy. So, okay. Is it clear what this algebraic construction is doing? Like, if you now hear the word twisting cochain, is it clear what it does geometrically? It's trying to compute the cohomology of something which is built as a vibration out of two guys. Okay?
Will you define what the Morikatan element is and what the relations are?
No, but I mean, it doesn't matter. Whatever makes this square to 0. It's just that if you're a fancy person, you can just call this a Morikatan. Okay, so what's the first step? So the minus whirl. So the minus whirl is the following. It's a whirl in which you're going to start with a manifold X, and you're going to have inside a Lagrangian, whose boundary is that of a Lagrangian lambda, and the Lagrangian filling, it's going to be exact. So we have it here. And now the minus stands for the fact that we're going to attach a handle. So actually, you're going to think all the time, if you want, that you're going to attach a handle and actually work in the manifold that we've been describing. I think Sebastian and Amiel a bit discussed that. So okay, so this is L, by the way. This is L. So now you can prove, or at least you can state the main theorem of their paper just by looking at this picture and this picture in here. So what should the main theorem be? Well, this is Yankee and Eckel Mikuli. So how should the theorem read? I have a compact Lagrangian, right? Which is L union the cocore, right? So I can call this Lagrangian. So we have the Lagrangian L lambda, which is just given by lambda union the core. And there's a second Lagrangian, which is non-compact. Remember exactly the picture I was drawing. And come on, I mean, this is also an analog, so the picture is exactly the same. I forget the genes. Okay, so there's a second guy, which goes in red, which is telling you that you might want to compute a wrap invariant in here. So let's call this C of lambda for a cocore. And then the second guy is the cocore. Then, what's the statement? I'm not going to state it, honestly. let's try to get there all together. What was happening in this cotangent bundle case, which at the end it was something about the loop space of a topological space and the topological space itself. It was that we had chains in X and chains in the loop space of X, and both of them compose in a way that whenever you twisted them geometrically, you ended up with a completely trivial topological space, whose chains were that of a point. Okay? Good. So now, well, on the one hand, here's the point. So that's somewhat relevant. And second, what kind of invariance do I have in L? Well, I have the infinitesimal standard thing, but I also have the wrap category, right? I can also compute wrap in L, forgetting about lambda. So now, what can we state? Well, if wrap of L were... Okay, let me put it this way. What is computing wrap homology of C of lambda, and sort of at the same time, the compact homology, Floer homology of L? Yeah, the wrap. Exactly. So, what's the hypothesis? Well, before the hypothesis was the total space was contractible. Now the hypothesis is wrap homology is 0. Okay, so then, if the wrap homology of L, whatever you want to, I mean, we can put it homologically. So if this guy has wrap homology 0, we have that the Floor chains of this guy, which at the very end of the lambda is the same thing as the infinitesimal Floor chains, so infinitesimal Floor chains of L, which you might want to think just as CF of this thing. So think of CF of lambda in this after surgery picture, is Cazul dual to, well, wrap that guy. Is this statement clear? Does it, just trying to, imagine you had never even tried to do that. You start with the tangent space, the tangent space, you do that example, and then you ask in general, when is this true? And what you have to do is you have to compute that. Now, just intuitively, I'll fill in the details, hopefully, if I have time. But what's going to be this co-twisting chain? So, this twisting co-chain. This thing that's going to go from here to the loop space and then acting on F. Well, in the talks today, we've seen that the wrap homology of L contains, on the one hand, internal generators for the compact part, and then the rep chords upstairs. But these fit into a complex. So you have the interior guys that go into the total complex, and then you quotient to the rep chords. The fact that Floor homology 0 is just telling you there is a connective morphism, and that's a chain. So that's it. Okay? Well, I mean, that's like page 60 in the paper. But okay? Is it clear that that's a geometric idea? That if you have this hypothesis, then this makes sense. And in particular, when I take the cotangent bundle and the fiber and the zero section, this recovers the Cazul duality with change on the space and change on the slope space. Okay?
I think your statement is not correct. Because this is not called Cazul duality. This is, Cazul duality you should be possible to recover the change on the loop space with change on your zero section.
Yeah, that's what this is doing.
But this is just you need some more addition. You need some additional assumption to make sure that.
Oh yeah. Okay. Well, okay. Yes. Yeah, but I haven't gotten into these details. Okay. So are you happy if I say simply connected L?
Yes.
Okay. Simply connected L. Okay. Okay. So now you've been able to state the theorem in the minus world. Let's try to state the theorem in the plus world. So the plus world is the one that Kevin was describing at the end of his talk. So the plus world is the one in which, well, either you think that you stop at lambda, or you actually think that you attach this infinite handle in here. Here. So that's the plus world.
So Cazul dual means there is a Maurer-Cartana element, so such that if I twist by that, then
that's a
I get zero.
That's a
homology.
Yeah. This is by far, I've never read that anywhere, but I think it's a reasonable definition. It implies whatever. When you take algebras, then it implies Cazul algebra. Okay. I'll get that. Maybe when I go to the algebra, we can do that. Try to do the geometry. Yeah, I think that's a reasonable definition for Cazul dual spaces. Right. Okay, so we have this thing in here, and exactly the same picture. We have this guy in here, and you now tell me who's playing the role of the red guy. So Kevin drew two guys, so you just have to decide which one is this. So, are we going with this one? No. Good, so this is the guy. Okay. So this is the lambda. And now the statement is going to be exactly the same. Like, if this guy is 0, then you have a Cazul duality between wrap of this guy, understood in the new place. So you can think of it as just the endomorphisms of this guy in the stop category, and then the infinitesimal of this guy. Okay? It's exactly the same statement.
What's the lambda supposed to be?
So this is, if you have a front, so you have something like that, this is just a disk filling this guy. Does it make sense?
Just a cocoa push.
Yeah, it's a cohort push down. Okay. Which has a unique augmentation. Unique geometric filling in here. Okay, so here's theorem. The same holds. So we have a duality. So maybe under enough vanishing of by 1 between wrap chains on this lambda and the Floor theory of the Lagrangian inside. So, or completed with that guy. So that's Floor chains. Note, by the way, that this doesn't even make sense as an object in the stop category, so you really have to compute an infinite one. Okay, good. So,
Let's say we have what?
duality. Yeah. Oh, it says under enough by 1 equals 0. If the Legendre is 0.
Missing.
Yeah, okay.
And duality, yeah.
We have a duality. Okay, here's the deal. This duality between changing x and changing the base space of x not only holds if x is simply connected. So whatever happens in topology, you gotta ask it here, because if you don't ask it here, it doesn't even happen in the case of a cotangent bundle. You just throw in this hypothesis. The Legendre is simply connected, and the Lagrangian field itself is simply connected. Okay, that's not a Flirt theoretic issue. It's a purely topological issue itself.
Okay. There's also a Flirt theoretic. We have to assume things about the real code, you say.
Yeah, so you have to assume that there's a bounded below degree for the generators, for instance.
No much is bounded, I should be positive.
Yeah. Okay. Yeah. Yes, I agree. Positive generators, but that's the algebraic analog of simply connectedness. Okay. If you have simply connected space, that's what the chains are going to look like. But yeah, I agree.
Excuse me. Can you re-explain what L is this the same L lambda?
Yeah, L is the same as M lambda, except that you now think of it in the new place.
Okay.
It hasn't happened. Oh, by the way, this is called the plus world.
And also, like, according to your philosophy, wouldn't you expect even if the wrapped floor homology of L is not 0, then there exist Maurer-Cartan elements such that if you twist, then you compute the wrapped floor of L?
You compute the defect.
Yeah.
Yeah. But I mean,
Is that also-
if you don't know the defect, then that doesn't tell you much.
So what's the defect?
No, I mean, you're going to compute the difference. You're going to compute whatever the wrap is doing. But, I mean, this is kind of a computational tool. This is kind of, imagine I want to compute something like, maybe you want to compute this. I'll talk in a second why this you can do it. And then you say, no, forget about this. I'm just going to compute that. So then I'm going to tell you now algebraically how on earth do you go from here to here. Because I haven't explained it. I've kind of talked about this duality, but I haven't explained how to transition from one side to the other.
But wouldn't that defect be the wrapped floor of L?
Yeah. Yeah, that's...
So if you need to...
Yeah, if you know 2, you know the third.
Fine.
But, okay, so can I erase this theorem? No? Okay, so now we're going to assume all the hypotheses we need to assume for this Gaussian duality to hold, both topologically, the degrees for the algebra, and the vanishing of the wrap. And the point is that in this minus world, we're going to have 4 invariants. So on the one hand, you have the Chekhanov-Eliashberg DGA. That's the DG algebra. Okay, and that's the usual old style DG algebra. Okay, it's counting those fellas with coefficients only in the homology, if you wish, of L. Okay, so like old style coefficients from the homology of edge of that. So this is the standard thing that has been defined twice, kind of. Okay. Okay. There's another guy in here, which should be by PE exactly this thing, which is the self ohms of C lambda in the wrap category. Okay? Now, what should this arrow be? Somebody shout. I just said it. What's this arrow? Kevin?
Sorry, I got lost just the first time.
No, okay, let's go again. Okay, we have the Lagrangian, we have the Legendrian, we have the Kokor. Okay? Now, right now I was talking all the time about this Lagrangian and this Kokor. Now we're going to throw in a third guy, which is this lambda. Okay? What's the point of that? Is that, well, actually, although you have attached a handle, you would have desired to do all these operations without ever attaching anything. Kind of the pre-surgery perspective. Okay? So in this column in the left, this is sort of pre-surgery minus world. Okay? And this is after surgery. So after surgery, it makes sense to talk about the Kokor, and it makes sense to talk about lambda, L sub lambda. Okay? So what's the thing that tells you that this DGA is exactly the Kokor? Exactly plus the minimum. B. Perfect. Do you approve? Yeah? Good. And then, what's causal duality telling you? Causal duality is telling you that this guy is related to the Flirt chains of, well, we were saying here, lambda, here, and then the question is, what goes here? And the point is that nothing special should go here. You shouldn't be counting new things in here. You should just count them in a different way, okay? And then what's going to go here is going to be something, which let's call it now this thing, LC sub-grading. And what's the property that these two have to have? Well, again, think back in the case of the cotangent bundle and just the zero section and the cotangent fiber. What was this? Well, this was change on the loop space, and this was just change. So whatever this operation is, going up, it has to recover kind of change on the loop space. Okay? When I say loop, it's always base loop space. Okay? So that's what I'm going to try to explain. Like, well, how do you transition from change on the loop space to the chains and back from the chains to the change on the loop space? Okay? And this has a fancy name. It's called Adams-Escobar construction, and then there's the bar construction. So that's what I'm going to explain now. Okay? And then these are going to be algebraic constructions that we're going to apply to these diagrams. We good? Okay. So just for the sake of structures, this is a DGA. This is going to be an infinity coalgebra. The difference between algebra and coalgebra should not bother anyone. You can just take the linear dual. So take the linear dual and just make it an infinity algebra. So this is an infinity algebra, and this is also an infinity algebra. Okay. So now I could exactly take all these things and put them in this plus world. Now you just gotta tell me what I have to do for this diagram to still be true in here. I mean, do we agree that everything will kind of fit if I just make the players be the correct one? So instead of C lambda now I'm gonna have D lambda in here. And then downstairs we're gonna have this fella, which I mean I really haven't defined, but it's gonna be related to this guy in the same way that chains of a space are related to chains on the loop space. And then we're going to have infinitesimal now. Okay, so this is Cazul duality, and this is PE, but now with a small adjective in front, which is puncture PE. Which, whatever, conjectural, whatever you want to think, just geometric picture. Okay? So, now, should this invariant be exactly the same as this invariant? Because, you know, in the pre-surgery picture, there's no reason whatsoever to know whether you're going to touch a handle or not. Okay? So what's the difference between that guy and that guy? All the questions I'm asking have been replied, you know, in previous talks. So I think it's hopefully not surprising. Yeah, where?
On that side.
Yeah, so where should the coefficients be?
In the
Chains on the loop space.
Yes, yeah.
Okay. Of who? Of lambda itself. Okay, so there's two ways to look at it. On the one hand, you can think, well, I'm actually just attaching a handle, but then at the very end, because I have this puncture, whenever I look at holomorphic disks downstairs, they can break, but because they cannot pass through the middle, these break-ins might not be adjoint. So you need to keep track of this local system of coefficients, okay? Now, you could also do that here. The only problem is when you do that here and then you attach a handle, that dies, okay? So, and I don't know from yesterday, but from a sheaf theoretical viewpoint, this is extremely natural. If you have some sheaf inside, which is microlocally supported on lambda, you can always take microlocal monodromy, which means that if you just think of this kind of diagram, and if I have a sheaf here with like C square, that's not going to be C square, it doesn't matter. Okay, so some stratum here. Then what's microlocal monodromy? Microlocal monodromy is going to be precisely assigning to this space this cone of this map, okay? So now you can start here, go around, look at all these cones all the time, and you get a monodromy. So this gives you a local system on lambda itself, which then you might decide to kill or not. But if you don't decide to kill it, then you have to have this information. Okay? So again, it's information you have, but in here it gets killed, and in here you must have it, because otherwise it doesn't get killed. So in here is with loop coefficients. So I'll probably now be horrified by how late I am. Yes. So let me just say a couple of things about how to construct this invariant and what are the delicate points. So first of all, you got to choose a nice model for the loop space coefficients. So these are loop space coefficients in the chains on the space of lambda. So first of all, there's lots of choices. So like singular chains, simplicial chains, CW chains, whatever, cubical chains. Okay. So take your pick. The point is, in here we're going to use lots of products. And that's the reason to take cubical chains. Cubical chains are the ones that are used most neatly in order to compose products. So whenever you open a paper and someone says, I'm going to use cubical chains, you should expect them to take products all the time. Okay? Because otherwise they just pick the wrong thing. Okay. And then there's another thing about these guys, which is the moduli spaces involved in defining the differential in here involve higher dimensional moduli spaces. So it's not only one dimensional thing in its boundary, but you're going to have chains on that loop space by the evaluation map. So you're going to have higher dimensional chains, which means you have to get now higher dimensional moduli spaces with all their breakings. Okay? So defined as it is, it's okay to define it, but it's very hard to compute because you got to see these higher dimensional families of disks. So I'm not going to get into that, lack of time, but there is another way to approach this VGA with these coefficients, which is through parallel copies. And that's an entirely different talk, how parallel copies translate the higher dimensional moduli space into rigid things, but now with these Morse perturbations that you have. Okay? So let me just say that if you really want to compute that, that's still okay. There's another way to define this invariant with parallel copies, and in the paper they prove it's the same. And essentially the same philosophy, the augmentation variety. Okay? This copies idea is kind of powerful. Okay, so, okay.
Augmentation category.
Augmentation. Yeah, sorry. Thanks. Good. So now let's get to the thing, how do you jump from here to here and back? Okay? And this is mostly algebra, but, it will have a geometric counterpart. So, this goes by the name of Adams covariant construction. So, the question that this answers is, how do I recover chains on the loop space if I only know chains on the space? And you actually forget you know the space, just kind of the algebraic structure in that. So this recovers the algebra meaning the whole infinity structure that you have in these chains. Maybe let me create it this way from the cochains in M. Okay, this is going to be an infinity coalgebra, co-augmented with inclusion of the point, and this is going to be an infinity algebra augmented just with a triple system, sent to zero. So how does one do this algebraically? Well, one takes whatever C you have, that's C, the infinity algebra, and now try to emulate purely algebraically what's happening geometrically. If I have a simplex in here, the first thing I do if I want to go to the loop space is think of it as having one dimension less. So the first thing you do is you take C and you shift this guy by 1. Okay? At the same time, because this is co-augmented, you can use the co-augmentation to kill that. This is just killing the inclusion of the point. And at the same time, you want to throw in the unit in here. So you're going to take unit element, this guy, and now what can you do with loops? Well, you can concatenate them. And because you want to recover the full A infinity structure, you got to throw in products of two guys. So now you're going to throw in this guy, tensor, this guy again. Okay? And now you understand how this goes now. Okay? So now in here I have to define two things. If I want this thing to be an A infinity algebra, or maybe in this case, I just want it to be a DGA / infinity algebra. Well, I have to define a product and a differential. So how is the product defined? So the product here,
Co-algebra?
algebra. This is an A infinity algebra with a Pointryagin product.
Sorry, so, what does bar over C mean?
Oh, it means take the kernel, the co-kernel of this co-augmentation.
Co-kernel of co-augmentation.
I mean,
Yeah.
okay, so product and differential. So the differential is just going to count exactly the infinity operations in here. So this is from the A infinity operations. And the product is that one. So this is just concatenation. The historical reason these things are called covariant bar is because instead of writing polynomials like that, people just wrote bars, and the bar meant you actually have to desuspend and then put them all together. That's the Allenberg plane notation. So okay, is it clear that this algebra has some chance at least to recover that guy? Okay, so now if M is simply connected, theorem, this algebra actually recovers this thing. It's quasi-isomorphic to that guy. Okay, if M is not simply connected, then you kind of have to do something. It is always true that this fella, when sees this the infinity coalgebra, is a completion of this guy. But you know, this means that this contains less information than this, because you could take this guy and complete it to this guy. Okay, but that's going to kill things like pi1 and stuff like that. Okay, so this is one construction, and you have the reverse construction. Conversely, the Kovar construction, so that's has an analog descending an infinity coalgebra, an infinity algebra, or a DG coalgebra. Sorry, it's called the bar construction. And what this does, whenever you see a B, think of classifying spaces. What this does is exactly the same thing that you try to get BG out of G. And geometric intuition is just you have a bunch of points and arrows, and that defines some simplex, which is non-trivial, and now you just keep iterating, killing it. So you think how Miller constructs BG out of G? Just as this category with a point and lots of arrows, one per each element, and then it attaches 2 handles to kill that, and then you attach 3 handles every time you have 2 morphisms being the same thing as the third one. Okay, and you do that infinitely many times till you get something which is like essentially EG mod G. Okay, which is BG. Okay, so this is again sum, where now you're going to put the things up. So you're going to reduce this with an augmentation, put it up, and now sum up. Such and such. Okay, so this is a bit of piece of algebra coming from trying to recover your topological invariant in an algebraic manner. So once we have that, we can actually state Gaussian duality in a proper way. So essentially, Gaussian duality is, well, taking either of the 2 guys, okay, and then taking modules. So it's about jumping from C to loops of C or from A to B of A. So in this sense, then we can use this to resolve any module, so any, say, A module, via tensoring with bar. So you take B of A, and then you just tensor with this guy. What this means is that suppose that I was computing something like this. So you take Rom over A of K and K, and this module structure is just induced by the augmentation. Okay, there's a map from A to K, and that makes this a model over that. Okay, please be geometric. I mean, this is just the intersection point of the two Lagrangians. This is just, you know, the L. It's very simple. So now, what does this mean geometrically? Well, Rom means I have to first do a resolution and then take the ohms, right? Well, what's the resolution of K? Well, a resolution of K is just given by taking this standard bar resolution. So that's going to be B of A tensor K, and then K itself. And now, wonderful thing that happens. What happens is if you do this and then back, well, nothing happens. So if it happened that your A was actually the loop of somebody, which
That's the tensor over.
that's the tensor over K. I mean, over A, but then, yeah, you can take it over. Take it over A. Then so if, and that's something that doesn't necessarily happen, but if A happens to be a loop of C, because then you can use that B of the loops of C is just the same of C. This is telling you that this Rom is just computed by Rom, which is, I mean, it's no longer Rom now, it's just a standard Rom, from C itself to K. So this is just going to be, well, the dual of whatever you want to know, this Rom, okay, the dual of C, the linear dual of C, okay? So what's the punchline here? Like, suppose you were trying to compute this thing, where this fella in here was the loop of somebody. What this gets you is exactly this somebody, with a certain duality. So in particular, so in the case that we were dealing with, where's my thing? In particular, you can now take and try to compute change on the space X, X is L, really, it's going to be Lagrangian, by doing this fella in here. So this is going to be loops on the chains of X, which for now we're just going to think of it as being by the Adams-Kovar construction this fella, and then KK. So the reason I'm going here, it's not because of pleasure, it's because that's what you're going to find on the internet. Okay? When somebody's going to define for you Koszul duality, is going to say, this is the Koszul dual of an algebra. It's R of K, and you're going to say, why? Okay? Hopefully this links it to the geometry a bit. This K is nothing more but the intersection between lambda and L, and this is what's supposed to be the RAP, and this is what's supposed to be the standard floor theory. Okay? I'll repeat that eternally until you guys are convinced, or at least believe that that might be true.
You said just what's
Okay, okay. Let me add a sentence. It's eternally, but there's 5 minutes. Okay, so this is always true. Okay, this is sometimes referred as the Eilenberg-Moore spectral sequence. Eilenberg-Moore, by the way, it's just telling you how to compute the homotopy or the homology of the homotopy fiber from the fibration itself. But the loop space is the homotopy fiber of the inclusion of the base point inside of X. And that's exactly what the Kovar construction does for you. So, you know, the Eilenberg-Moore spectral sequence is nothing but apply the Kovar and then filter appropriately. Okay, but this is the geometry behind it. Okay, so in particular, this is always true. And in some circumstances, so again, if pi 1 is nice and everything, you also get the other thing. I'll forget about the chains and cochains, which is you take our of this fella as a k as a module over this. Okay, and then you get this thing. So that's the way you jump from one to the other.
Sorry, also there in the first line that's chain or cochain? It's just that you dualized on the left.
Let me think. It's chains. Yeah. Okay. Now it's cochains.
Let's go chain also.
Okay, now it's consistent. Okay. So hopefully this picture is clear, and this is kind of the classical way to jump from one to the other for the case of loop spaces. And now what you can do is, instead of writing these, you write floor homology. So in our world, so the floor world, like the world. What do we have? Well, the picture is the following: is we're going to have our Lagrangian here, lambda. Then we're going to have our filling, L. And now you either are going to have this kind of pseudo co-core, or you're going to have, you know, a handle and an actual core. Right? I mean, I think you're attaching, or you just push this guy out. So maybe let's call this still lambda. Okay? What's the core geometry that we're discussing here? The core geometry is that this fella has one intersection point, and that's this k. And now the point is that this k can be seen as a module over the endomorphism algebra of L or over the endomorphism algebra of the other guy. And hence you can play this game of jumping from one to the other. And that's going to happen even only if, well, RAP of L in this case is 0. Okay? So in here, K is played by ohms in the appropriate guy category. So it's either stopped at lambda or it's either the partially wrap or the fully wrap, depending whether it's plus or minus. It's in here by L and C lambda. And this is at the same time a module over LL and C lambda, a module. So this is standard flow chains, either infinitesimal or else compact itself. And now ohms of C lambda, and that's going to be wrapped if this actually is D lambda, and it's going to be stopped, or it's going to be fully wrapped if this is C lambda itself. So now you can ask, I take Floer chains, I look at this guy as a module, and now I ask what are the ohms of this guy to itself, taking into account L. And now you see the geometry, because this is literally telling you what are the ohms from here to here, what are the things from these points to itself. If I'm allowed to think of it as a module over the Floer homology of L, then that means I can go to the interior. and then you keep going around. So you're going to get disks and the evaluation map on the loop space of L from them, depending on the situation. If there's nothing else, then RAP is 0. Okay, but that takes into account intersection points, and vice versa. I mean, if you have this cohort in here, and you're thinking of that guy as being a model over here, it means that you're going to count this, that also take into account the RAP homology. Okay, and then the causal duality is that whenever you do this operation, which is R Floer homology of L KK, that recovers the RAP homology of the cohort, and R of the K with itself, thought of as a module over the RAP case, that recovers infinitesimal Floer homology. Is this too much? Is this okay? Does it make sense so far? Okay. So now I was going to do some examples. What would you rather me? To shut up, do examples, or continue with general theory? Examples. Examples. Okay. So, first example. So, that should be familiar to everybody. I really believe we've covered this week. So, let's take something simple, which is the N naught. So, lambda is going to be just the boundary of the standard flat disk inside of D to N. It's going to be X, lambda the N naught. What should this picture recover? This picture should recover exactly what we started with. The RAP homology of the co-fiber, sorry, the tangent fiber, and the zero section. Why? So if we're in the minus world, so if in the minus world, that means we're going to attach something into lambda, then x of lambda is just going to be, well, whatever this thing is, let's start at minus 1. Are we comfortable with that? I'm taking a ball, taking the knot, attaching a handle to it. And then I have two Lagrangians. Zero section, which is this Sn minus 1, and the cotangent fiber, which is exactly the C lambda, which is the cocore. So whatever. No, because it's the boundary. Oh, you're right.
Yeah.
Because it's not the boundary. it's so maybe Sn is the n plus 4. Thanks, Marco. Okay, so in here, do we need to take loop coefficients or not? No, right? Because you're capping, so whatever local system is going to die off anyway. So no local coefficients, and then you just have the standard picture. So there's going to be one rep chord, and in here, oh, I didn't say a fundamental thing. Okay. So in here, we're going to have this invariant, and now we're going to have this invariant. Okay? Maybe that's a good moment for me to explain how to go from one to the other. These two guys count exactly the same things. They just count them and gather them in a different algebraic way. This counts the differential, and the differential of one fella is a product of a lot of people. This instead, it's an A-infinity coalgebra. And what it does is, it just gathers the strips that go from 1 to 1 in the first coproduct. Like in the well, that kind of, I don't know if to call it that product, from one guy to itself. It gathers a strip that goes from 1 to 2 of them in the second operation, and then in the third. And how do you go from here to here? You just take the sum to the differential. And actually, the A-infinity relations here is exactly the same equation that being del squared equals 0 in here. Okay? So that's a good way of never writing an A-infinity relation. You just take covariant and say L squared is 0. Okay, so in here you get to choose. So for instance, if we had this model, we can also throw in, a K, but so maybe, let's say, so either of these models is okay here, no loop space. And then we're going to get one rep chord and some index. And then you can throw in an idempotent just to make the algebra match. Okay, so that's what the Legendre is seeing. And now, what is the Floer theory seeing? So there's a way to pass from here to here. Just, oops. What is the Floer theory seeing? Well, the Floer theory is going to be that of L lambda. So now L lambda is going to be Sn. So in here, we're just going to have something with a maximum and then a minimum. So then the Floer chains on the Sn, those are just going to be constituted by a minimum and then a maximum. Okay, And now the crucial question, which I'm aware it's hard at this point because I haven't given much detail, but what's the twisting cochain that goes from here to the looping here? Okay. Do we at least agree that we should be able, if you want to prove that these two are Cazul dual, okay, which is the pre-surgery prescription of those two being Cazul dual, what you gotta do is you gotta check what this means and take loops. But this thing was the same thing as this thing. So what you gotta do is to find the twisting cochain that was there that was going from here to the loop space on the floor, for instance. Okay, I'm gonna write this out. So now, a way of going from here to checking this is Cazul dual, it means you gotta find a twisting cochain from here to here, right? A map from here to here that then you can deform the tensor product with. So need a map, twisting cochain tau, that will go from LC inside of CE, but this CE, by going to the other side and taking the after surgery perspective, I might as well just think that this map is CF. And I really should be adding idempotency in both sides, but let's not take this thing. And in this case, what's this map? Well, what's the loop space of CF? It's just going to be some polynomial algebra on the maximum, which is one generator. And then this guy in here has only one rep chord. And so, what can you do? I mean, it's this rep chord goes to this maximum. And that's a twisting thing that once you take the tensor of these and twist with that element, it's going to give you an acyclic thing.
That seemed like the wrong.
Sorry?
Which direction is your map?
This way. I mean, it's, you can define it the other way if you want.
Okay.
It doesn't, you can take linear duals of that. So in here I was saying that the red chord in here is going to get mapped. So because in here you also have the red chord, it's going to get mapped to the maximum. And this means that when you form the complex, so when you do CL star and then loops on CF, that thing twisted with this tau has differential such that the differential of a word, so let's call this max A, and then let's call this chord C. What are elements in here? So these are elements of the form A to the K C, or just A to the K, for K non-negative. And then the differential of an element which is A to the K C. Well, what's that? The differential doesn't do anything because there's no enough degree to do anything. But then it's going to send the C with the tau to the A. So this thing is sent to A to the K plus 1, which makes the complex acyclic. So acyclic. And hence, Cazul duality holds between the zero section and the cotangent fiber. And algebraically, this is telling you that the change of the loop space, which is a polynomial algebra, is Cazul dual to just k of x mod x squared, which is what this guy is. And this is an exterior algebra. And that's what you're going to see in kind of 50s algebra books. That the Cazul dual of an exterior algebra is a polynomial algebra and back. That was the first instance of Cazul duality. Hence Cazul duality between, let's say, exterior algebra on one element y and the polynomial algebra on this element. Okay, so I should put this down. I had another example prepared with one positive and one negative component. Maybe, do I have a minute to just recap everything? Okay, so it's like, given any situation, you're going to have invariants attached to the Legendrian, and you get to decide whether you put loop space coefficients or not. If you put loop space coefficients, then you have two choices. Either just think theoretically and use higher dimensional moduli spaces, or use, for computational purposes, parallel copies. That's one way of doing things. Now, why would I ever want to present these counts with del square equals 0 in such a cumbersome way such that they are presented as the covar of something? Well, the reason is that because when I take R of k as a module over this CE, that thing is going to be precisely the guy that when you loop gives you that guy. So what you can do is you can regather the counts of the DGA that gives you the CE, in terms of this A infinity coalgebra. Geometrically, nothing is happening, just regathering. Okay, you're putting loop space if you're in the plus world. You're not if you're not in the plus world. So that's what defines this felling here. Okay, and you can think of this as some sort of causal duality. And so computationally, essentially, if you knew the DGA, then you just try to find this by hand. That can be done in the case of the hop link. It's pretty easy. And in the other way is even easier. If you understand this very well, these operations one by one, then you just take the Kovar construction. So everything is simply connected and everything. So this is the pre-surgery perspective. Alternative, you can go and attach the handle, or just make the thing stopped at lambda. And now you're going to have two kinds of invariants. The wrap of the co-core, or at least this that was in there, and then L itself, which is either going to be compact or is now going to go to infinity. And then what you do geometrically is you look at the intersection point and you think of it as being modules either over the full homology of that guy, which has to be wrapped, wrap and stop if it's d lambda, or just wrap if it's c lambda. Or you think of that guy as a module over the compact guy, or the infinitesimal that goes to infinity. And then you try and compute R-om of this module either over one guy and the other guy. And the point of this paper and the point of this duality is that these guys are going to recover each other under simple connectedness of lambda, simple connectedness of L, and vanishing of HF, CW, HF in the right category. Okay, that being said, a very easy hypothesis for that is that the category you're working on itself has zero Hodgkin homology. Another way to put it, if you're working in a flexible or in a subcritical Weinstein manifold, then symplectic homology is zero. The wrap is a module over that. So in that case, this always holds. So in that case, this is always going to be true. And for instance, you get pretty spectacular things. Well, not spectacular, but some wasn't observed before. Is that if you have a Legendrian sphere, and now you go and try to compute its Chekhanov-Eliashberg DGA, if you assume it's simply connected, then necessarily what this is telling you is that this algebra is going to be the same if it has a filling L, then change on the loop space on the completed L. Okay, so that's a way of computing that. And just to answer Sebastian's question, like this morning, was it you?
About the calculation.
How to compute, yeah. Everything wraps around. So what you do is you want to compute sometimes Hodgkin homology of something. And in this case, you want to compute, for instance, Hodgkin homology of the category, which in here, if you generate it by the fiber, that's Hodgkin homology of the change on the loop space, right? And what you said was, well, change on the loop space, that recovers symplectic homology. It's the Hodgkin homology of that, that's the free loop space. Agree with that? No?
I'll have to find.
Okay. So symplectic homology equals Hodgkin homology of the category. Okay. That generated by the co-fiber, the contention fiber, which means that's Hodgkin homology of the loop space. Now, please nobody be surprised that the Hodgkin homology of the base loop space is the free loop space. Because recall this Hodgkin homology was just deformations. And if you don't have the base point, you can just deform by reparametrizing. So clearly that's the deformation of the base loop space. So then you have Hodgkin homology with base loop space thing. But now by this guy, change on the base loop space, which was the wrap endomorphism algebra, is the same thing as the endomorphism algebra of a compact object. And that's the point, that you get to compute now the Hodgkin homology of a generating thing by a Morse theory. Okay, because you're going to have like Floer chains on just your compact Lagrangian. You see? You've gone from a non-compact thing to a compact thing. And maybe that's the end. Thanks for listening.
Any questions or comments?
Can you repeat what in the plus word, what was the CF of the filling? What was that?
Oh, the infinitesimal. Because the wrap doesn't make sense.
Yeah, but it was both are infinitesimal, so it's
Oh, but I mean,
in the
it's with the plus. I mean, you go left and you add them in. Like in the minus, you're just going to take L and just have one min or one max. Okay, so you're just going to displace the Lagrangian to the right. Okay, it's the same difference between cochains on L and cochains on L relative to the boundary.
There is something with the coefficients, the loop space coefficients stuff.
No, you don't need loop space coefficients.
And the DDA has loop space coefficients.
DGA has.
I mean, constructing outplus requires loop space coefficients.
Okay, then probably.
But then I can get it together in my head what is filling, what kind of coefficients we use with the filling.
No, but I thought the loop space coefficients came when you went from the filling to this co-core.
But the loop space coefficients are a bit different on the filling, and it's more than on the knot itself.
Yeah, that's true. So you say we should do infinitesimal CF with loop space coefficients on L. That might be. I mean, that being said, that's not covered in the paper, but
Yeah, right. Maybe there's something.
yeah, okay. So this is pure speculation. This is
maybe it's not about some kind of Lagrangian filling. Maybe this is just about the knot lambda itself.
yeah. I mean,
it's like when you delete the co-core, you're just seeing lambda there. I mean, you're like trying to go around the co-core, and if you try to go around, it's like you're going around lambda.
yeah. No, I mean, what is
It
true
doesn't have to do with
is what
that.
you're saying. It has to do with lambda, and it has to do with this kind of co-core. It has nothing to do with the L itself.
So maybe the L wasn't so.
No, I mean, yeah, and the L, it's all my fault. Like, it's in the paper they never discuss L
So
in this setup.
Think about lambda in this case.
Yes,
Or
I think
about lambda.
yeah. To be completely correct, in that case, you should only think about lambda and d lambda, and then relate these two as Cosol dual.
Okay, then I'm not.
Okay.
Thanks.
But still, there should be a theory that extends to the L inside, and we can think about that. Yeah, that's good. Okay.
Do they obtain a new calculation using these methods?
So you can calculate this empirical module of like A of the n over 5.
No, but this was done already by Yankee
Yes,
before,
yes.
so kind of not new. No, I mean, I don't know. I mean, this is my opinion, but to me, this paper kind of sheds light, like structurally, on what on earth is happening, and particularly the invariance coming from compact things versus invariance coming from smooth things. There's this duality between smooth and proper, and that's just kind of explaining in which cases this duality holds. They have two interesting examples, one given by Lenny and another is the trefoil, which is what happens when things are not simply connected. And in the case of not simply connected, well, for the trefoil, in which you have a filling which has genus, in there what you can prove is that the map into the completion is injective. So somewhat you get to recover some information. But then Lenny gave an example, which is, I mean, this force in particular to be commutative, and I think it's like 7-2 knot or something that had a non-commutative DGA. And
I forgot.
you forgot.
No, that's right. That's right.
Yeah, I think it's 7-2. Anyway, so in some other examples, you're not able to actually recover. Doesn't seem you're going to recover anything. Certainly, the map to the completion is not injective. It's kind of an interesting thing now. When duality doesn't hold, when does it recover some things, and when does it really kind of fail? And yeah, it's about.
It's not understood how it fails. If it's
No, and I mean it's pretty clear geometrically what you have to do. You have to really understand the connecting morphism, right? And so it's going to be some kinds of holomorphic disks, and in some cases those guys exist, and some guys they don't. That I mean, the trefoil we understand very well. Other guys, I have no idea. But I think that's interesting. I like it. Okay, we should call.
All right, good. Go jump in the lake.